So yesterday we talked about the wing, okay? And come on in. I need you to draw a cross section of an airfoil. What we talked about yesterday.
Oh, okay.
All right. Yeah. Go ahead and draw it.
Wait, how? Just with the plane here and the wing?
No, just don't even bother with the plane. Just draw the airfoil itself. The teardrop looking thing that we've drawn.
Right.
Okay. Yeah. Go ahead and draw that.
What is that?
Pretty close to it. More like
Lemon.
try making it more round right there.
Think of a lemon. That? Do you want us to draw it too?
Okay, good enough. Good enough. All right, we got it. Okay.
It's like a weird.
Yeah, it looks good. It looks good. Okay. The airfoil itself, really a cross section of it. What you'll want to do is you'll want to round it out a little bit, and if you got to, draw it and redraw it until you got this basic shape. Because I assure you, this is not the first time I'm going to be asking you to draw something like this. Okay, so we got the basic shape of an airfoil. Okay. Now let's go over some terms. What was the mean chord line?
In the middle, like the very tip, or not tip, but the first edge of it, I guess.
Okay, right here?
There, all the way through the...
Right there.
Yeah.
Okay, so that was a chord line. Okay.
Is that your asking?
So that's your chord line.
Right.
All right. And then what's camber?
The
Just the curve.
The curvature. All right. So you got camber here, and then you got camber here, right? Okay. And then what's your mean camber line? It's an imaginary line that you're on it. Oh, right, it's an imaginary line where if you would take the average of these two curvatures, then it'd basically be, or in this case, I think it'd be kind of pretty close to your chord line right there. Okay, so that's your imaginary line. Okay, so then this part of the wing right here is known as the what edge?
Leading edge.
Okay,
Leading edge.
good. This trailing edge. All right, now the part of the wing that connects to your fuselage is known as...
Wing root.
Okay, and the part of the plane that is the part of the wing that's away from the fuselage?
Wingtip.
Wingtip. Okay, good deal. Okay, let's start talking about some different terminology here, okay? And we're going to stick with the wind right here. Now, what they have is they have what's known as the angle of incidence. Okay, so write that down, angle of incidence. Okay, so angle of incidence. Now the angle of incidence is the angle, and make sure I got this right. Right, that's what I thought it was. Okay, it's the angle between the wing chord line and the horizontal of the aircraft. Basically the aircraft's longitudinal axis. Okay, so what I mean by that is that you're going to have your aircraft right here. It's going to be sitting on the ramp. It's going to be sitting on the jack stands or whatever. Okay, your aircraft itself is going to be set up. Now your wing, your angle of incidence, is basically the angle that they put in the aircraft between like if you were to draw a line from the very top tip of the aircraft to the very back, and then when they put the wing on it, okay, you see how that works? And your chord line is not going to be this extreme, but your chord line is going to run like this. Okay. So it's not going to be synced up with the horizontal of the aircraft. Okay, that angle right there is known as your angle of incidence. Okay, and this is important to know.
So the chord line doesn't line up?
Right, the chord line of the wing will not line up. Now, sometimes it will. It depends on what the purpose of the aircraft is. But generally, the term between the chord line and the longitudinal axis of your aircraft is known as your angle of incidence. Okay. Now let me ask you, why do you think that things such as angle of incidence would matter. Right, go ahead.
It all depends, like, the purpose of the plane. Like, the more angle you have, the higher lift you'll
Okay,
get.
good, good. The more angle you have of what?
Of the wing, like, when it faces, so you won't have to put such a high angle of attack. It goes.
Okay, angle of attack. That's the term we're looking for. Now let's go ahead and talk about angle of attack. So that's the next thing you want to write down. Go ahead and write down angle of attack. All right. Now your angle of attack is the angle between your wing chord line and your relative wind. Okay? So it's the angle between your wing chord line and your relative wind.
Is what now? Say it again.
It's the angle between wing chord line and your relative wind. Yeah, hang in there, guys, and make sure you write these down, because these are gouge items, okay? This is stuff that you're going to be tested on, not by me, but by the FAA. Okay, so your wing chord line and your relative wind. What do you think relative wind is?
Which way the wind's blowing?
Yeah, the wind, so in comparison to what, though?
The direction you're going.
Okay, and the direction you're going is known as what? It's a path, right?
Vector.
Okay.
But what type of path?
Flight pattern?
Flight path.
Flight pattern.
Okay, a flight path. Okay, so this wing is going to have a flight path. Okay, and this flight path is where it's actually, and I mean, it sounds like I'm kind of breaking it down, but I assure you I'm breaking it down because it gets deep. It gets a lot deeper than this. But, okay, so your flight path is basically the direction that the wing's going. Okay? Duh. I mean, we're going forward, so our flight path is going to be this way. Okay. So we'll just draw the flight path. Therefore, your relative wind will be the wind opposite and parallel of your flight path. So if the wing is going this way, or your flight path is this way, then your relative wind is going to be opposite and parallel of your flight path. Okay. Everybody hanging in there so far?
Parallel with what? So,
Parallel with your flight path. Yes.
some water real fast.
Yeah, go ahead. Okay, so parallel and opposite your flight path, right?
So that's if you're flying straight, though, right? Or does it stay the same if you're flying up?
Okay, well, we're about to get into that, okay? So right now, this would probably be like a zero angle of attack, okay? Now, when your angle of attack increases, okay, so when they're talking about that, what they're talking about is your flight path, your angle of attack. So I'm going to draw another, hopefully my camera will be able to get it from here. That thing's got mad peripheral vision. But, so what we'll do is we'll draw another airfoil with a slightly higher angle of attack.
What's up, guys?
Hey, what's going on?
All right, after class, if you guys can all come to the air wing, we're going to write down your activities, okay?
Yeah.
Cool? All right. David, you're going to fly today, all right? At 5, all right? All right, go. You're right after school. If you want to just get your stuff and come over, and then you can get, come here, please. Oh, bit of shit. Hubbard, you're on next week, okay? Early, so I'll let you know. You got something today?
Am I good? Do you know you are?
Come in again and let him, Colonel has all the information, so
All right.
find it. I think you're flying too, Parker.
When's
Okay.
tomorrow at 1 o'clock?
We had to change it. You're going to be next week early, all right? Because we got to get still some of your paperwork in.
Alright.
Cool?
So,
No,
this Friday?
just this Friday. Okay. All right. Cool.
Good deal. Okay. So this is going to be an extreme example of an extreme angle of attack, but we'll just work with it because everything's great. So you take your chord line of your airfoil. Yeah, come on in. So you take your chord line for your airfoil, right? And then so your chord line's here. All right. Now don't make the mistake of thinking that where the airfoil is pointing is what your flight path is going to be, because where your chord line is and where the airfoil is actually going is two different things. So in this case, you got a high angle attack, but the plane's going this direction. It's going forward, or it's going, okay, not forward, but it's going in that direction. So your flight path is going to be this direction. Okay, so here's your flight path. All right, that right there is your angle of attack. I'll use different colors. Angle of attack. See, I already blew it. See, that right there is your chord line. Yeah, hopefully I didn't. Okay, so that's your flight path, that's your chord line. So your relative wind would be coming equal and opposite of your flight path. Well, your relative wind is going to be equal and opposite of what your flight path is. So you see how it starts changing up? So you got 3 different elements that you're having to work with here. All right. All right, so, and I'll just go ahead and draw straight through the airfoil. Okay, so then what we're working with here is the angle between your chord line and your relative wind is known as your angle of attack. Okay, so if y'all got to draw this, you go ahead and draw it down, but that's it, okay? And your angle of attack is primarily what's going to determine how much lift you get out of your aircraft. Okay, so that being said, y'all can probably get another better understanding of why you have the angle of incidence, or why they'll put a little bit of, make the chord line a little bit higher than put a little bit of angle between your chord line and your longitudinal axis of your aircraft. So when you're rolling, trying to get up to takeoff speed, go ahead.
So with the chord line going to the flight path, would that be the angle of incidence?
The chord line going to the flight path.
Yeah, like when it goes to the angle of that.
Right, the chord line going to your flight, oh, you're talking about the angle here, between your flight path and your chord line, right?
Yes, sir.
Okay, well, in general terms, you can consider that the same thing as your angle of attack, because your relative wind is going to be opposite and parallel of what your flight path is, okay? So I'm just drawing these arrows on top and the bottom of each other to kind of, show it, but in all purposes, if you really wanted to kind of okay, this line right here can be both your flight path and your relative wind.
It'd be the same angle because it's just basically going out further.
Exactly.
Yeah.
So, but what I do is I draw, but I want you to think of it in 3 separate concepts, okay? Because it's 3 different entities you're dealing with, even though for practicality terms, your flight path and your relative wind, it's opposite and parallel. But, and don't get confused, because like when you get into a stall situation, or when you get into you want to think of your angle of attack in relation to your relative wind, and that's all it is. It's the angle of attack in relation to your relative wind. It doesn't have to do with your horizontal or your horizon, or it doesn't have to do with anything else, okay? Because one of the questions you'll get, and we haven't started talking about stalls yet, but people will start thinking of stalls of your angle of attack in relation to the horizon. When it's not that, it's the angle of attack in relation to your relative wind. So you can technically be in a dive, for example, and be in a stalled condition, or you can be, at a nose low attitude and be in danger of stalling out.
I remember us doing that. That was fun.
Right, exactly. So there's a bunch of different things that can bring about that condition. I don't want to get too ahead of that because I just want y'all to kind of get this general knowledge in your head. Okay. Let me see. So that being said, there's a few other terms that I'll start bringing them up when we start getting in that part right there. But okay, let me see what time it is right here. Okay, it's about 2:38. Man, time's going way too fast. Okay, so anybody got any questions about this? No? All right. Let me go ahead and erase this. All right. Now, when we start talking about lift, there's a few things that we bring up. We bring up Newton's laws of motion. Okay, Newton's 3 laws. Now, y'all guys are taking science here, so does anybody know what Newton's 3 laws are? What's the first one?
I don't
What goes
know
up?
the numbers, if any, but isn't one, for every reaction, there's an equal and opposite reaction?
Okay, that's the third one.
Okay, good.
But the first one
Wait,
is...
an object in motion.
Objects in motion will stay in motion unless acted upon by...
Right, so objects in motion will stay in motion. So objects in motion will stay in motion. Will stay in motion unless acted on by
Under the force.
outside force.
Right.
Basically, so it's got its inertia, and unless something, it starts trying to affect its inertia, then it'll basically stay in motion. Okay, so what's the second law?
Objects at rest will stay at rest until acted upon by an outside.
That's the first one. That's the first one.
Rest.
Yeah, rest. Basically, it'll stay in its state. So basically, what they mean by that is that, like, let's say, and they always give you like the cue ball example, or maybe the something, but basically you have a cue ball that you hit with the pull table, right? It'll keep going unless something affects its motion and cause it to stop. Usually the wall or another cue ball. At the same time, the cue ball at rest will stay at rest unless something affects it and causes it to change its state of motion right here, which is basically a standstill. Okay, and this actually ties into the concept of lift, which we'll start talking about in a little bit, okay? So objects in motion will stay in motion unless acted on by an outside force. Objects at rest will stay at rest unless acted on by an outside force. Okay? Everybody got that? Okay, just think of the cue ball example. You just draw like a little pool ball sitting at still, and then another pool ball with an arrow pointing at it. Okay. Now, what's the second law of motion? Nothing? Crickets? Okay, no problem. I've been there before.
Wait, isn't the
I kind of touched on it a little bit. It has to deal with mass. And we talked about this, the difference between weight and mass. Does that kind of...
Well, isn't it like the amount of force required?
Okay, you're very
And
close.
The amount of mass required is
What's the formula? Force equals...
equals mass
mass
over.
over-
No,
No.
Oh, I think I'm thinking of acceleration.
Yeah.
You got it. That's exactly what it is.
Acceleration.
Mass times acceleration.
Yeah.
Okay, force equals mass times acceleration. Okay, so force equals mass times acceleration, right? Okay, so force equals mass times acceleration. All right, so what does this mean? Well, we know what the mass of an object is, right? What is mass?
No, much space it takes.
Right, well, it's displacement in space, basically, or it's density, if you will, or how much material is actually in a object. Okay, so that's mass. All right, why is mass different from weight?
Because weight is the amount of gravitational pull.
Right, the attraction that a celestial body has on another object. So, the Earth has its gravity, the Moon has its gravity, everything has its gravity. We're being attracted towards the Earth, directly towards the center, okay? So your weight's going to change, okay? Does weight change?
Yes.
Okay, yeah, you bet it does. Yeah. G-forces will change your weight. Altitude will change your weight. Being on the moon will change your weight. So yeah, your weight's going to change. Does mass change?
No.
No, it doesn't. It doesn't change unless you lose an arm or something, or Okay, cool. So mass is not going to change. So your force that an object is going to exert, how much force that it puts on another object, is a factor of its mass multiplied by its acceleration. So it's force equals mass times acceleration. What's Newton's third law?
Every reaction, there's the opposite reaction.
Right, for every action there's an equal and opposite reaction. Exactly. Okay.
That's what I said.
So what is that? So what does that mean to anybody in here? Can anybody kind of give me a description of that?
You throw something.
Newton balls.
Hmm?
Newton balls.
Let's just say you push someone, there's the force of your push and then the force of gravity.
Well, you're going to push on somebody, and what's going to happen?
They're
They're
going to try to
gonna
regain
go
their
away.
balance.
Well, right, but their body's gonna push back against you just by their weight. So, like, let's say I try to push this. Okay, yeah, I can move it, but then I have to brace myself, right? Because to a certain degree, this is pushing back against me. You gave an example. I didn't quite catch your example.
Newton pause, you ever heard of that?
No, what is
It's
that?
the
Newton's
little,
cradle?
Yeah, it's those like
Like,
five
you
little
drop
balls,
it.
and you have
Yeah,
you like push,
balls.
pull
And you
two,
push
and
one.
they hit and two
Yep.
go.
Right, okay, there you
And
go,
it's-
there you
and
go.
the balls in between absorb the energy and it brings
then
it
it
on
just
the other side, and
passes
the other
it
one
off.
comes out.
Right. Okay. So that's a good one. That's a good one.
That's
Anyway.
just so badass. I love that.
So yeah, so that works out. So that's why it works. For every action, there's an equal and opposite reaction, and the key term being equal and opposite. Okay, so force in, force out, or push in, push in. Now you can put force, but no work's actually going to be done unless you actually make a movement. Okay, so for every reaction, there's an equal and opposite reaction. Good. That's how jet engines work, basically. All right. So, okay. 2:45, we got 5 minutes. So we're going to go. Okay, so anybody got any questions about that? Write that down, because that's a gouge item. Yeah.
So what was the third one again?
For every action, there's an equal and opposite reaction. Okay. Now, what we got now is we got Bernoulli's equation. Who's heard of... Right, okay. You've heard of Bernoulli's equation? Okay.
That's what I've forgotten it a long time ago. You have to remember that.
All right. Well, basically, in layman's terms, when we start talking about Bernoulli equation, it kind of talks in the lift, but it talks about how a fluid interacts around a solid object, either a solid object moving through the fluid or
Floating.
well, yeah, but we're talking, yeah, exactly, yeah, floating, but moving through the fluid. Basically, either the fluid moving over and around the object, or the object moving through the fluid. Okay, so, well, the popular example that they talk about with this, without really going heavy into the math, what you do is you take your pipe, right? So you take your pipe right here, right? Okay, and then you have a fluid moving through here, which generally what we do is we use water as an example. Air will basically give you the same results, but we use water. So what you do is you put the constriction in the middle of the tube right here. Okay, so you see the constriction right there? And then you move the water through it. Now what's going to happen is as it goes through this constriction,
Speed up.
right, because why?
Because constricted pressurizes.
Right, exactly. So what it's going to do, and it's not it's not like the water's smart or whatever, and it's like, oh, well, all my buddies are here and I got to get it over here. It's just it's just basically how the water functions as a mechanical force. So basically, it's going to speed up around the constriction due to the curvature, and then when it gets out on the other side, right. So wherever you have constriction, the fluid's going to speed up, and it gets a lot more complicated than that. But this is basically layman's terms right here. So then you can measure it in velocity pressure. Okay, so you got two gauges, right? You got velocity, you got pressure. Velocity, pressure. Okay, velocity, pressure, right? Okay. So what do you think is going to happen? Okay, so for velocity, for every unit of velocity, you're going to have a given unit of pressure. Okay, so velocity is, basically at the midpoint, your pressure is, you're going to have a corresponding amount of pressure. Now what's going to happen is that when you get to the constriction, what's going to happen to your velocity? It's going to increase. So velocity increases, and then what's going to happen to your pressure? Is it going to increase?
Yes.
Your pressure decreases. Yeah, it decreases. Yeah. So your pressure decreases, and then you have a corresponding back into it. So then your velocity is going to go
Down.
well, your velocity is going to, go back down, and then your pressure is going to go And actually, that's a bad sign. I should go ahead and use equal signs. I think that'll work out. So velocity is equal to its pressure, velocity up, pressure down, and then you have velocity equal to its pressure. Okay?